Hi, I'm Jon Benedict, hydrogeologist for the Nevada Division of Water Resources. Thanks for attending this session covering some of the work that's being conducted to better understand and quantify the impacts of streamflow capture on the Humboldt River and its tributaries. My follow-up talk to Kip and Mike's presentations focuses on how the results from the capture and water valuation study inform and in some cases poses challenges to the development of conjunctive management practices to deal with capture and potential conflicts to surface water rights caused by groundwater pumping in the Humboldt River region. In this presentation, I hope to accomplish two things. First, I want to illustrate and describe a few of the key conceptual results from the capture and water valuation studies described by Kip and Mike that will be important considerations for any conjunctive management approach developed for the region. Second, I want to describe some of the potential management approaches that have been proposed or suggested to tackle the consequences of surface water-groundwater interactions in the Humboldt River region. I've broken down this talk into three general sections. In the first, I'll briefly provide some context on the capture problem. In the second section, I'll take a dive into examples of some of the results that serve to inform, limit, and hopefully assist in defining and implementing management approaches in the region. Finally, I'll talk about some of the approaches proposed by the state engineer and perhaps some suggested by other stakeholders to manage potential conflict in the Humboldt River region. I'm now going to turn off my camera because I've got a lot of information packed into the slides. Fair warning, some of the charts and tables that I show are in draft form and intended mainly as examples of the kind of results we're seeing. Hopefully the information and explanations provided by Kip and Mike's presentations will serve to fill in some of the gaps that I may have in that regard. Thanks. At the very beginning of this session, Levi provided a pretty good summary statement of the problem that we face in the Humboldt River region, and I'm not going to repeat that. But I've chosen to keep this slide in my presentation for those watching and simply for the record because it does a great job of summarizing the problem. That said, a relatively recent event that is significant with respect to how this capture problem plays out and is worthy of discussion is the settlement agreement reached in 2020 between the State Engineer's Office and the Pershing County Water Conservation District. The essence of this agreement is that in exchange for the PCWCD withdrawing their 2015 lawsuit that alleges conflict and requests that the courts step in, the state engineer will develop a draft order to define certain administrative mechanisms for conjunctive management going forward. So what is the specific context in this settlement agreement as it relates to best available science? That is, what does the agreement require with respect to using the model to assist a management framework? First, the model would be the science tool to help figure out how to avoid conflict. Second, the state engineer would develop a draft order describing how new groundwater applications would be reviewed and considered as informed by the model and consistent with a conjunctive management approach. Third, the draft order would also lay out mechanisms to address future conflict between existing groundwater and surface water rights, insofar as curtailment is concerned. As an update, by the time this presentation is made available, the draft order corresponding to the settlement agreement should be publicly available. And I'll return to the substance of that draft order near the end of this presentation. But first, I want to illustrate a few examples of model results that will likely inform the development of management approaches moving forward. Some of these charts are probably familiar to you. I think Kip showed a few of these in maybe different format. On the left is a map of the Humboldt River region with each of the three separate models highlighted in different colors just for reference. To the right of that map are what I'd call sort of the big picture model results from each area, and they're set in a side-by-side manner for comparison purposes. The charts along the middle plot annual pumping in blue and annual capture in red for each model. The upper model's at the top and the lower model's at the bottom. And I think it's important to note that for each of these charts, the scales are orders of magnitude different on the y-axis. What I really want to point out here is the relative size of the red columns, which are capture, compared to the blue, which is pumping. As you can see from these plots, and also you can see from the summarized 2015 results to the right of the plot, in the upper model, capture as a proportion of pumping is substantially larger than in either the middle or the lower models. This observation makes some sense because the upper Humboldt watershed is characterized by more than 100 tributaries that feed into the main stem, making it much more likely for groundwater wells to be near to and impact one or more of these tributaries. But this really needs to be looked at more closely in light of the fact that different model designs have different resolution and different capabilities as required by data limitations. So we've got to look at this in a comparative way. Without going into detail, I guess the take-home message here is that capture impacts are greatly influenced by watershed characteristics, but potentially also by model limitations, and we've got more work to do here. So we're finding that capture is a function of watershed characteristics. That's not unexpected, but it requires additional examination due to the data limitations of those watersheds, including a lack of seasonal streamflow data and also the model resolution. We're also finding that capture is dependent on streamflow being greater during runoff seasons and lower as the flows diminish. And this is also true for longer time frames, meaning that capture is greater in wetter years and smaller during drought periods. We're also finding that median flow estimates can be used to reasonably characterize long-term capture, suggesting that while it's less effective when considering our predictive capture impacts during any given wet or dry year of any given irrigation season, an appropriately calibrated model that uses generalized information can reasonably predict overall long-term capture. So I finished with my brief illustrations of how model results are beginning to flesh out important characteristics of capture that are needed to assist in managing groundwater and surface water conjunctively. Now I want to provide a similar illustration with respect to the UNR water valuation study. As many may know, the original purpose of this UNR study was to determine the cost of conflict to support mitigation regulations, whose approach was to manage conflict by assessing fees to responsible groundwater users and then pay compensation to affected surface water users whenever conflict occurs. I'm sure Dr. Taylor's presentation has covered the results of this study fairly thoroughly, so I'll just use a single example here to illustrate at least one relationship from this study that may assist us in better understanding how different magnitudes of conflict and how conflict on top of drought, for example, may affect the economic conditions of ranchers and farmers that depend on surface water for their livelihood. This chart plots a value of water to an alfalfa operation for a hypothetical conflict under varying prices of hay. As might be expected for the alfalfa farm, the higher the value of their alfalfa crop, the more valuable their water. Likewise, the longer the conflict persists, the more valuable their water becomes as well. Now this is because of the lack of water in one year adversely affects next year's production and or operation decisions that need to be made, resulting in compounding the loss of profit in successive years. But how does a result like this, and for that matter, the entire UNR water valuation study and its results, play into conjunctive management in the Humboldt River region? Well, for one thing, it does tell us that there's no single value for water. Also, it's simply a valuable first step in understanding the economic impact of water shortages. It's certainly improvable with additional feedback and vetting from the farmers and ranchers within the Humboldt River region. It's also improvable by modeling the relationships between seasonal water availability, for example, and seniority of water rights, which can be done. Or, for that matter, by additional modeling of other types of operations up and down the watershed. I want to stress that currently there's no formal proposal to use either compensation or assessment fees as part of future management approaches. That said, such concepts may still have merit, particularly if the funding were used to support steps to help fix the problem. But even if compensation to surface water irrigators or assessment fees to groundwater pumpers is not part of the management approach, understanding the economic effect of potential conflict or any kind of water shortage is important context for understanding and managing this problem. Most of this session has been spent talking about measuring capture and measuring the value of water. But what about what is arguably the most important measurement regarding this problem, the measure of conflict? Measuring conflict seems simple in concept. It's the difference between scheduled deliveries, or what a user is scheduled to get based on priority and water availability, and actual deliveries, what he actually gets at the head gate. Measuring scheduled deliveries is achievable, at least historically or operationally. That's exactly what our water commissioners do every year to manage the system. What about the actual deliveries? For farmers in Lovelock, it's somewhat achievable because they're at the end of the system and the M-Lake gauge is available. But it's not so easy the further upstream you go. Take an area like this picture near Winnemucca. Here deliveries can include overbank flows and diversions into or from sloughs. Further up in the headwaters, there are hundreds of smaller diversions with a variety of diversion structures with limited capability to actually accurately measure flow rates and durations. Is it practical or achievable to define farm or ranch specific conflict? Even if we accurately measure deliveries, how do we separate the amount of water lost due to natural seepage from water lost to capture as the water flows downstream? As an alternative to requiring instrumentation and accurate measurements of deliveries at every diversion, wouldn't it be more effective to use models to assist in determining what proportion of capture represents conflict on a more regional scale? If so, perhaps a more regional level management approach is also more practical than attempting to define and manage impacts to each and every surface water user in the Humboldt. But what is it that we know about conflict? Well, we know that conflict due to capture may occur at any surface water diversion along the drainage system that's downstream from groundwater pumping that causes capture. We also know that the users at the end of the drainage system are more likely to feel impact due to being last in line and due to the compounding effects of drought and the cumulative impacts of groundwater capture everywhere up and down the system. We also know that the capture model will be able to assist in determining and predicting regional scale conflict, but predicting or even measuring actual site-specific conflict may not be achievable unless surface water users upgrade delivery and diversion infrastructure. And even then, it will be a challenge. As we approach the completion of efforts to characterize stream flow capture and the impacts of capture in the Humboldt River region, what are the implications of these results to management approaches, and what's happening on the management administrative side of this issue? First, I want to stress again that the studies being completed did not explicitly tell us when, where, or how much conflict may occur in any given year. The capture model can certainly provide insight to that, but capture, which the model characterizes, is not conflict unless it impacts the water availability of a senior user when his right is in priority. That means that while we currently can administer new applications to prevent additional impacts and avoid additional capture, we cannot yet appropriately deal with existing groundwater rights until we develop a means to, at a minimum, predict the likelihood and approximate amount of conflict during any given year into the future. From my perspective, this remains a key missing link that's needed before we can address administering water rights in a manner that avoids conflict and reduces long-term impacts from capture. Second, it's important to say that there are any number of possible steps, mechanisms, and approaches that have been suggested or used by other Western states to deal with conflict linked to streamflow capture. And several are listed on this slide that should continue to be considered as we become better able to characterize conflict using best available science. In this slide, I've subdivided some of these out into general categories. But how does the draft interim order dovetail with these concepts? For my final set of slides, I'd like to spend some time walking through the mechanisms proposed in the draft order designed to prevent additional capture by new applications, and also the framework described in the draft order regarding how the state engineer would consider curtailment decisions going forward. Over the last 5 years, our office has been evaluating new applications using a relatively simple analytical tool to conduct streamflow depletion analyses and determine capture impacts that would be caused by any new appropriation or change application within a 5-mile distance of the Humboldt River or a tributary. In this case, those new applications would only be approved if the analysis indicated no measurable increase in capture. But as described in the draft order, we're now proposing alternatives to outright denial of such applications, so long as potential conflict is prevented by offsetting the predicted capture using either replacement water or by withdrawing a portion of an existing groundwater right. I'll describe each of these alternatives in the next few slides. The first approach is to use decreed surface water to offset capture caused by a new application. So how would this work? In the example shown here, the proposed well, which is shown in the graphic in the lower left, is predicted to capture water based on the blue curve on the plot in the upper right. This blue curve would be derived using the capture model, whose results will be made available to the public via the USGS capture query tool. In this hypothetical case, the plot predicts capture that increases up to about 9 acre-feet after 50 years of continuous pumping. If the applicant were able to secure decreed rights that were of appropriate seniority and amount to offset the capture, conflict would be avoided and the groundwater application could be granted. In this illustration, the predicted deliveries from an 1870 right, again showing on the left here in the table, for about 0.045 CFS, are actually shown in the orange bars in the plot. And these can be estimated based on historical flow records. What they show is that overall, this replacement water would exceed capture, but it also shows that there would be likely several years where, due to drought, the replacement water would actually not be served. This illustration shows that while not perfect, a replacement water approach can be a reasonable option for avoiding conflict. Another proposed mechanism is withdrawing a portion of an existing groundwater right to offset increased capture predicted by a new application. In this example, the proposed change in point of diversion would move a water right closer to the river, and assumedly the model would then predict an increase in capture from the river. In such a case, if the application, for example, were to move 10 acre-feet of water to the proposed well and then withdraw 1.6 acre-feet from the existing well, they could offset the increase in capture, conflict would be avoided, and the groundwater application could be granted. In this illustration, the predicted recovery of capture due to withdrawal are shown in orange on the graph to the right, and indicate that while in the first few years of the capture would not be offset, but in the near term and long term, recovered water from the withdrawal would exceed cumulative capture, and additional conflict would be avoided. And similar to the replacement water approach, the capture impacts could be retrieved directly from model results that would be made available to the public. The tools described in the previous two slides only currently would deal with new appropriations and change applications that move groundwater rights closer to a surface water feature. They're not designed to help reduce or prevent potential conflict from capture caused by historical pumping or existing groundwater rights. Currently, largely as a consequence of the lack of support for our 2019 mitigation regulations, the State Engineer's Office has taken the approach of holding off on defining specific long-term management practices until the modeling effort is complete and we and the affected water users better understand the magnitude and distribution of capture impacts to the Humboldt River and its tributaries. However, the draft interim order provides for the fact that curtailment of junior water users may be necessary in circumstances where either curtailment is effective at increasing actual flow within the time frame of a potential conflict, or perhaps when curtailment is the only available tool to effectively relieve persistent conflict caused by cumulative impacts of capture over time. So the draft order outlines a proposed framework for the state engineer's approach regarding when and how curtailment would be contemplated. That outline is summarized here on this slide, and it points to certain considerations that could alleviate the need to curtail, including consideration for aquifer storage and recovery projects, water conservation plans, or perhaps other statutorily available mechanisms. If you want to read the draft order, by now it should be available on the NDWR website, so I encourage you to go there and take a look at it. I want to close now with a compilation of approaches or mechanisms that have been suggested by surface water and groundwater users, other stakeholders, and the state engineer's office. Some I've already mentioned, others I haven't, and I'm not going to now. But my sense is that as we continue to improve on our understanding of the problem and our ability to measure conflict, capture, and the cost of conflict, more informed management approaches can and will be spelled out and hopefully implemented. I'd also like to say that key components to achieving a successful outcome include this list of 3. 1, maintaining engagement and working with the stakeholders and the surface water and groundwater users and the communities in the Humboldt River region to inform and also to seek input on solutions. After all, it's their livelihood that we're addressing here. 2, we need to continue to improve on and use best available science in our management and administrative practices. 3, we need to use an adaptive approach that acknowledges that the problem can't be resolved overnight, and that the state engineer's office can only administer solutions that are statutorily available to him. That third acknowledgement means that new approaches either need to fall beneath the umbrella of existing water law, or there needs to be thoughtful revisions to the statute that would flesh out acceptable conjunctive management approaches that have the support of the public as well as their representatives in the legislature. In closing, thanks much for attending this session. I hope you found it useful, and I'd also like to thank Tina and her staff at the Nevada Water Resource Association for the great work they've done organizing and producing the 2021 annual conference. If you have any questions about either Kip Allender, Mike Taylor's, or my presentations regarding the Humboldt River region effort, please join us on Monday, January 25th at 10:10 for a live Q&A follow-up session. I hope to see you there.